In this problem, we want to derive the equations of motion, the natural frequencies, and the mode shapes of this autonomous system. And specifically, we want to find the equations of motion in terms of our x's, x1, x2, x3. We're going to see through this problem that the system has three independent degrees of freedom. So we'll get the three equations of motion in terms of that. And it's going to turn out the natural frequencies, the mode shapes, which are coordinate invariant, won't depend on what set of three degrees of freedom we use, but we'll derive it in terms of the x1, 2, and 3. So we want to find it will turn out three equations of motion, our three natural frequencies, and then their associated three mode shapes. We will have to start with the model of our system. We are not given the mass matrix or the stiffness matrix. There's no dissipative elements in the system. There will not be a damping matrix. So we want to use Lagrange's equations for this. Now if we see the system, we are treating it as the autonomous system, which actually doesn't matter in terms of the natural frequencies or mode shapes, but I'll get rid of these forcing terms. We're just going to consider the autonomous version of this system, and actually we'll follow up with this example later where we will give it initial conditions and we're going to solve for its behavior. So we're going to need to look at the total kinetic energy and the total potential energy in our system. We'll start with the kinetic energy here. And looking at the system, we have three elements in the system that have mass and or inertia. We have the block M, we have the block 3M, both of those can only translate vertically. And then we have the pulley, which can translate vertically because it's attached by a spring to the ceiling, so it can translate up and down, but also the pulley is able to rotate about its center of mass at O, so it will also have rotational inertia, which gives it rotational kinetic energy. So let's start with the easier elements, looking at the M, which has a degree of freedom attached to it of x3. So its kinetic energy will be 1/2 times its mass of M times its velocity of x3 dot squared. Right, the x3, x1, x2, and theta degrees of freedom here are going to all be from inertial frames, so they are not going to be moving. If we move on to the 3m and look at its kinetic energy, again it's translational, it can only move vertically, so it will be its mass of 3m, and its velocity is already marked for us as x2. So that gets squared. And then the pulley, which has the translational kinetic energy and the rotational kinetic energy. Let's look at the translational one first. We are given that it has a mass of capital M, and in the translational direction, it can only move vertically, and we have denoted its deflection vertically as x1. So we have 1/2 times its mass of big M times x1 dot squared. And finally, we want to account for the rotational kinetic energy of the pulley. So that's 1/2 times its mass moment of inertia. I'll use J naught for now, but we are told to make J naught equal to mr squared over 3. And that will get multiplied by its angular velocity squared. Its angular position about its own center of mass at O is theta. So we're going to use theta dot, and that gets squared. Now, before moving along to the potential energy, let's look at this kinetic energy term. We have an x1, 2, and 3. We also have a theta, all of them the time derivatives. But in the prompt, we are to derive the equations of motion with respect to just the xi. That means x1, 2, and 3. If we look at our system now, the system has only three independent degrees of freedom. Even though we have 4 marked here, and for convenience in deriving our kinetic energy, and we'll see in the potential energy, using this theta term is going to be helpful, but we will need to substitute it out. But if we look at how the 3m block is attached to the pulley, it's just attached with that rigid wire or cable. There's not a spring between the 3m and the pulley. So if we look at what the behavior of x2 looks like, it is not independent. We cannot hold x2 at 0 and then freely move the rest of the system. So if we imagine holding x2 at 0, we cannot change the value of x1, that vertical deflection of the pulley. We can't change because of that rigid connection it has with 3m. Same thing with theta. We can't, if we hold x2 at 0, we can't rotate the pulley. We can't change the value of theta without changing the value of x2. Now, x3 is different. We can change that independent of the others. The value of x3 will not influence x1 or x2 directly, or theta, but x1, 2, and theta are all intertwined together. So it's going to turn out that only 3 of these degrees of freedom are going to be independent. Again, for the purposes of this problem, we'll use x1, 2, and 3, but really we could use, x3 would have to be part of it, but we could use x1 and theta, or x2 and theta, and we're going to get different equations of motion because we are solving for different degrees of freedom. However, we will turn out to get the same natural frequencies and the same mode shapes, even if we use a different combination of these 3 degrees of freedom. So we're going to need to see what the relationship is between theta and our other degrees of freedom, so that we're going to be able to substitute that out before we go into Lagrange's equations with this. But we'll come back to that after we derive our V, our total potential energy in the system. Looking at the system, because we're ignoring the gravitational potential energy, there's only going to be 3 elements that have potential energy in our system in the form of spring potential energy. We have the spring at the top K, we have the 2K spring, and we have the 3K spring. Let's start at the top with the K spring. That one will be pretty easy to solve here. So if we look at the K spring, at the top it's attached to the ceiling, and at the bottom it's attached to O, which has a degree of freedom x1 attached to it. So spring constant of K, and only one side of it's moving, so it's going to have a deflection of x1 squared. And that one will be pretty straightforward. Let's go to the 3K spring next, which will also be relatively easy. So I've marked the top and bottom there. At the top, it's connected to x3. At the bottom, it's attached to the floor, which does not translate. So if we account for its spring potential energy, 3K is its spring constant, and that will just be x3 quantity squared. And finally, we have the 2K spring. This definitely is going to get a little more complicated than the other 2 springs here. So we'll have a 1/2 times a 2K times. Now again, we have to consider, in this case, what degree of freedom, positive or negative, is going to cause 2K to go into tension. So if we account for tension at the bottom and at the top, this will give us the correct quantity inside to find the net deformation of the spring. Starting at the bottom, it's attached to x3. So if we just hold the top at 0, the top still, what sign on x3 causes it to go into tension? Well, since x3 is pointing down, that's going to be a positive x3. If the top is held still, a positive x3 will put the spring 2K into tension. And let's look at the top of the spring. So the top of the spring is connected to that pulley, and this is going to take a little bit more consideration here. That top of the pulley is going to translate based on the translation, the vertical translation of the pulley, which is attached to x1. x1 is defined as positive down. So again, if we hold the bottom of the spring still, how do we put the spring into tension? Well, we can put x1 negative, which would cause the pulley to go up, which would put the spring into tension. So a minus x1 will go into this quantity. However, that top of the spring is, again, attached to the pulley. The pulley is able to not only translate up and down with x1, but it can also rotate by theta. So there's actually 2 degrees of freedom at the top that can cause the spring to go into tension, the x1 and a value of theta. So based on where this point is attached here, if we had we've considered the pure translation of the pulley, x1, now we want to consider the pure rotation of the pulley. So the way that theta is defined here, if we rotate it by a positive theta, that point in pure rotation is also going to go vertically up, which is going to be putting it into tension. And because we're using a small angle approximation here, the top of the spring is connected to the inside of the pulley with that radius of r. So if we have an r times theta, and it's positive, that pure rotation also puts the spring into tension. So there's an x1 element and a theta element here that is causing the spring to go into tension. So we've now accounted for all three spring potential energies here, with the 2K spring just having that complication at the top, that the top of it can move due to theta and it can move due to x1. But on the inside of that quantity, we're accounting for all of the signs of those degrees of freedom that are going to put it into tension. So in our V equation, we still have the issue that we have a theta. In the T, we have that theta dot. We're going to need to get rid of those. So we're going to see what is that relationship we have between theta and the rest of our degrees of freedom. And I think it's easiest to look at x2 and see how x2 is going to be affected by other degrees of freedom. And then we'll be able to differentiate it to get rid of the, as we'll see, the theta dot term. So if we look at x2, because it's rigidly attached with that wire to where the pulley is, it doesn't have a spring, x2 is going to be completely determined by other degrees of freedom in the system. And similar to what we just saw with the spring, the 2K spring, we can consider how is x2 affected by, we'll see x1 and theta. x3 actually won't have any direct influence over x2. But we can see here, let's say that x1 is positive. So if the pulley is moving down, automatically, if it's in pure translation, the 3m block is going to move down by that exact same amount. It has to move with the pulley. It can't move independently because there's no spring there. So if the pulley is in pure translation, x1 is going to equal x2. They both move by that same amount. However, the 3m is attached to the pulley, and it's affected not only by the translation, but like the spring, it's going to be affected by the rotation of the pulley. So let's think of the pulley in pure rotation. If we go by an amount theta, if we rotate it by an amount theta, 3m is going to lower by an amount of 3r times theta, again, assuming small angles of rotation there. So we can say it's x1 plus 3r theta. And this is accounting for the x1 term being the pure translation of the pulley and the theta being the pure rotation of the pulley. And we can superimpose them together and we know exactly how x2 is behaving. And again, x3 can be completely isolated, but if we know x1 and theta, we automatically know x2. And if we take any of these two, x1, theta, and x2, if we take any of those two variables, we automatically know the third one because of this relationship. So we could, one option would be substitute out the x2 and replace it with x1 and theta, and we will get t and v in terms of our independent degrees of freedom. But we were asked here to derive the equations of motion in terms of x1, 2, and 3, so I actually want to isolate theta. So I'm going to rearrange this and say that 3r theta is x2 minus x1, and then I can get theta by itself is x2 minus x1 over 3r. And that will be the relationship between theta, x2, and x1 that I will be able to substitute. And if I take the time derivative of both sides, I will be able to substitute it in my t equation. R is constant, so it's not going to be affected. If the radius of the pulley were a time-dependent variable, then this would get more complicated. We would have to use quotient rule in order to do this, but I'll be able to make this substitution in t and v. So I can do it algebraically now because I'm going to do use Mathematica to do my differentiation for each of the three independent degrees of freedom, x1, 2, and 3. But I'll actually let Mathematica do the algebra for us as well, and we'll see that makes it a little bit easier. So I'll start with the Mathematica file from the previous example and fill it in so I don't have to retype everything. But let's fill in the t, and I can fill it in just as it is right now. And we'll see that Mathematica can do some of the algebraic substitution then automatically. So the second term is the 1/2 3m times x2 dot squared plus 1/2 capital M x1 dot squared plus the 1/2 j naught, which I will also substitute out in due time, times the theta squared, which I can use that theta dot squared. I'll run that just to make sure it looks correct. All right, so we have all four terms there, and we have x1, 2, and 3, and the theta dot squared. I'll wait to do the substitution a moment. I will fill in my v while I'm here, so 1/2 kx1 squared plus 1/2 3kx3 plus 1/2 2k, and then I have this quantity x3 minus x1 plus r theta of t, and that whole thing squared. And I'll leave it in that form for now. Okay, so this is the t and the v as I derived them using the convenient degrees of freedom, which there were 4, but we see that only 3 of them are independent of each other. So I can't put them yet right into Lagrange's equations to get my equations of motion. I'm going to need to sub out that theta first. So what I can do is I can go back up to, I'll start with the v, and say, use this slash dot, which is going to be telling it to use a replacement rule. So my replacement rule is going to be based on that coordinate mapping. So I'm going to say replace theta, and I'm using this arrow, this goes to, and just what I have on the page. So x2 of t, and this should be a theta of t, minus x1 of t over 3r, and end that. All right, so again, the slash dot is saying, it can be a list here, it's only one replacement. This is telling it in this equation, everywhere you see theta of t, replace it with x2 of t minus x1 of t over 3r. And let's see how that changes when I evaluate it. So now this equation, we see it got rid of theta and it replaced it with, well, this exact rule here, the x2 minus x1 term over 3r. So now v at least is in the right form. I have x1, I have x2, I have x3, and theta is gone. So I want to do something similar to t. I want to use my other replacement rule, which is really just the time derivative of this, that everywhere you see an x dot, replace it with the x2 dot minus x1 dot over 3r. And we see that Mathematica did the algebra for us, and we don't have to do all of that by hand, which we would normally be doing. And now our t equation, we see we have x1 dot, x2 dot, x3 dot, and that is all looking good. The other thing I can do here is I can replace the j naught while I'm here. If we look, we were told that j naught is mr squared over 3, to use that for this equation. So I'll do that replacement. J naught is mr squared over 3. So mr squared 3. And now when I run it, it gets rid of that j naught, and we're left with what it is in terms of m. So back to our modeling step. Now we can do our 3 Lagrange equations. I can differentiate the t and the v. I'll give myself some extra room here and get the 3 equations of motion. Again, we'll use Mathematica to do it, but I want to set up what we're actually doing. So del t del x1 dot plus del v del x1 equals 0, because we are doing this as an autonomous system. And then the second equation of motion will be the same thing, but everything in terms of x2 and x2 dot. Equals 0, and then we'll get the result out of Mathematica. And then we differentiate everything with respect to x3. So back in Mathematica, we have the t and the v in the way we want it, And I just copied these from the last example here, doing the 3 Lagrange's equations. So notice this is just in Mathematica syntax exactly what I wrote down. We differentiate with respect to x1, x2, x3, and out will pop our 3 equations of motion, the scalar equations, which then I want to put into matrix form. So running all of this, this is what we get, and I'll come back and put in the matrix form. And I'm already doing that collect, so everything's being collected in front of my 3 degrees of freedom that I am trying to track here. So I'm going to transcribe this to do it by hand, so then I can put it into the matrix form. So I pasted from the Mathematica, so I can, again, write it by hand and put it in the order that I want. So looking at the top equation, that was this first partial derivative with respect to x1. So we have this 28 over 27m x1 double dot minus a 1/27th m x2 double dot. And then we have the k terms, or the x1, 2, 3 terms. So 41 over 9 k x1 minus 8/9 k x2 minus 8/3 k x3, and that equals 0. From the second line, a negative 1 over 27 m x1 double dot plus, here we have a 3 little m plus m over 27 x2 double dot, and we have a minus 8/9 k x1 plus 2/9 k x2 plus 2/3 k x3 equals 0. And the third line here, this is where we have an x3 double dot, and this term has no x1 or x2 double dots. Getting into just the x terms, negative 8/3 k x1, 2/3 k x2, and a 5k x3 equals 0. So I'll take these 3 scalar equations and write out the equation of motion in that matrix form. So we're going to have a 3 by 3 M matrix times our X double dot plus, and then a 3 by 3 K matrix, leave some extra room here, times an X, and that will equal the 0 vector since this is an autonomous system. And I'll leave some extra room for M. Okay, so the first row of the matrices, we just have to look at that first scalar equation of motion. So in front of the x1 double dot, we have 28/27 times m, and that's the x1 double dot term, and then a negative 1 over 27 m is the x2 double dot, and then a 0 x3 double dot. I'll actually pull out the k from this matrix, so it's a little bit less to write since everything is going to have a k with it. So 41/9 times x1, and also that k, a minus 8/9 times the x2, and a minus 8/3 times the x3. Again, the right-hand side is 0. Coming down to the second equation, negative 1 over 27m is the x1 double dot. The 3 little m plus big M over 27 is my x2 double dot, and again a 0 term for x3 double dot. We have a negative 8/9, a 2/9, and a 2/3 k in front of x1, 2, and 3 respectively, and the right-hand side is 0. And finally, the third equation, we have no x1 double dot, no x2 double dot, and just a little m times the x3 double dot, and a minus 8/3 k, 2/3 k, and 5k times our x1, 2, and 3, and right side is 0. And I'll write this out explicitly. This is then our mass matrix times our x double dot plus our stiffness matrix k times our x equals 0. And before we go on, let's just make sure, or do a check now on the mass and stiffness matrices. They must be symmetric for them to be correct, or at least if they are not symmetric, we know they are not correct. Looking at the mass matrix, we only have to look at these off diagonals here. They are both negative 1/27 times m, so the mass matrix is indeed symmetric. And this is actually the first example we're seeing where we have non-zero off diagonal entries because of the coupling of the rotation and the translation in this system. All the other entries are 0 off diagonal, so it's symmetric. And then checking the stiffness matrices, or matrix, we have negative 8/9 on that off diagonal, positive 2/3, and negative 8/3 on that off diagonal. So the stiffness matrix also is symmetric. Get rid of these, get rid of some clutter, but they're both symmetric. And then we can identify what we have so that we can go forward and find, so we actually have the equations of motion step done. We are going to want the natural frequencies and the mode shapes. But based on the equation of motion in matrix form, we have a 3 degree of freedom system, which again falls under multi-degree of freedom and how we want to solve it. It's linear since we can put it into that matrix form. It is undamped. We have no dissipative elements in the system. Our C matrix is the 0 matrix. And it's free or autonomous. Our right-hand side is the 0 vector. Now we can go on and we can get our parameters, which for this system, we're not looking for the closed form solution yet. We'll do that later, but we want the natural frequencies and we want the mode shapes, which we'll do using, I'll actually do it both in Mathematica and I'll do it in MATLAB. I want to show it in MATLAB because that's where we're going to pick up later in this example to solve the system. I don't think Mathematica does quite as good a job once we want to find the closed form solution of this. Now, back in Mathematica, and we'll look at the basically same idea when we're in MATLAB. I'll put in the values for the matrix now. 1/27 times m, 0. 1/27 m. And again, I'll be able to use that substitution rule to put in numerical values. I renamed big M as m sub p for the mass of the pulley here so that I didn't get confused with the extra variable names. So that is my mass matrix is now big M, and MP is the mass of the pulley. And looking at the K matrix here, I can put that little k on the outside and then put in the rest of the matrix as I have when I wrote it down. Negative 8/3, negative 8/9, 2/9, 2/3, and then that last row, negative 8/3, 2/3, 5. All right, so I have m and k defined in variable form, but now I can put in the given values for some of these. So the mass of the pulley, we were told to use 4 kilograms, so I'll use that substitution notation, and the little m will be just 1. So putting in those rules, now we have numbers for m, and for the stiffness matrix, we can let k go to 20 newtons per meter. So everything is in base units here, and we have the value for k. All right, so these are matrices, it just doesn't show them as well, so let me suppress that for a moment. Now I want to do m inverse times k because I want the eigensystem of m inverse times k. I want the eigenvalues, I want the mode shapes, or the eigenvectors as well. So I can compute that, just want to make sure it looks okay in the form that I think it's going to be. So that's my m inverse times k. And finally, I can get, just like I did in the previous example with this, the natural frequencies and the mode shapes. All right, so it's trying to do it in exact terms, so I am going to tell it to instead do a decimal approximation. So that's what the //n is doing, is saying, all right, don't try to do everything as a rational fraction, just do a decimal equivalent, and now we see we have these decimal equivalents here. And on top of that, I can set the precision here to be lower. Actually, I don't even need that n now. So the set precision is going to say, do this calculation and only display 3 significant digits when you do so. And that didn't work quite as expected. Okay, now it does. I'll leave that // n in there. And then the same thing here. I only need to look at 3 digits for the mode shapes too. All right, so more importantly at the moment, let's look at the natural frequencies. It's putting it in actually descending order. It found the natural frequencies of this system with these parameter values to be 0.514 radians per second, 3.78, and 10.4. And that found the 3 mode shapes. So keep in mind here that Mathematica always tries to make 1 the last entry, and that will look different than what we have in MATLAB, which I'll bring up in a second. Our natural frequencies will agree exactly, maybe to a little bit of rounding error, but we should get the exact same natural frequencies in MATLAB as we get here. And actually, I'll do it in MATLAB in a second just to verify that. And then the mode shapes we get out of MATLAB will look different, but they are just a different scaling of these mode shapes. Now in MATLAB, I'll do the same thing that I just did. I'll define my M and my K matrices the exact same way I just had them, and I'll find the eigenvalues, and I'll find the eigenvectors. Now here I am using I will sort them in ascending order, since that's the way I do like to write them out. And that means I will also have to sort the eigenvectors correctly at the same time. So let's just run this and see that we do get the same results, maybe with a tiny bit of rounding difference, but these are the 3 natural frequencies, the square roots of those eigenvectors. So 0.514, 3.78 about, 10.42. And compared to what we have from Mathematica, these are more or less the same. Again, I told explicitly Mathematica to just return 3 sig figs, and that's why they're going to look a tiny bit different, but it's the same numbers. And looking at the eigenvectors, they are different out of Mathematica versus MATLAB, but again, MATLAB makes sure that the magnitude of each one is equal to 1. I'll actually record the ones out of MATLAB since we're going to be going forward with that in the subsequent example, but we do get the same basic results. So I pasted the results out of MATLAB just so I could transcribe them here. So my natural frequencies in ascending order, 0.514, 3.78. I'll just keep the 3 significant figures, radians per second. And then the mode shapes, I'll write it in matrix form, negative 0.170, negative 0.985, and 0.0408 with 3 significant digits, 0.830, negative 0.144, 0.539, and then the last mode shape, negative 1471, just keep the 3, a 0.0398, and 0.988. So let me just mark these explicitly. This is the chi1. It goes with what I'll call omega 1. This is my omega 2, and this is chi2. And this is going to be my omega 3, and this is my chi3. So again, the associated eigenvalue and mode shape or eigenvector must match. Even when I sort them, they still have to match each other. So at this point, I have answered the question. I have my natural frequencies, all 3 of them in ascending order. I have my 3 mode shapes. I got my equations of motion. So as far as I needed to find, for now, I am done with this problem. But we will revisit it and apply initial conditions and look at the behavior of the system. Now I want to look at one more feature of this. Again, I was told to derive the equations of motion in terms of x1, 2, and 3. Let's see what would happen quickly just in Mathematica if instead I derived everything in terms of, let's say, x1, x3, and theta. So instead of x2, let's use theta. So a different grouping of 3 degrees of freedom. They still completely describe the system though. Right, so I'll take everything I did and copy it because I just want to change some things in the second way I'm doing this. So now, instead of theta being replaced, I'm going to replace the x2. I'll actually do it here. So going to v, x2 using this equation instead, I'm going to say is x1 of t plus 3r theta of t. And I'll rerun this so it's a little bit more compact. Okay, and then I want to do the same thing for my t equation up here. Make that replacement with x2 dot will be x1 dot and theta dot, and rerun that for t and v. Right, so now with that other replacement, getting rid of the x2 and replacing it with x1 and theta, now we see t and v have x1, x3, and theta, or the time derivatives of those only. So x2 is gone away. So now I would do my differentiation with respect to x1, and then here would be theta instead of x2, and then my third one, theta dot, or x3 and x3 dot, that's okay. So rerunning all of this, we get different equations of motion, which should be expected because everything is now in terms of a different set of 3 degrees of freedom. So I do have to redo my m and my k, but I can do that quickly looking at what I have for these equations. So keep in mind the way I did this is I have x1, theta, and then x3 are going to be the order that I put my unknowns, that I put my degrees of freedom in. Right, so for the first one, I'll just copy and paste. And that'll be an MP there, so that's the x1 double dot. And then I have the theta double dot will be the second column. And paste that in, and that looks okay. There's no x3 double dot, and then my k's are going to look different here. I have a 3, a -2, and a -2r. So r comes into play here. Oh, I did that in the wrong order. This should have the r because it has the theta, and then this has the x3. And I guess here I should redo these since I went through things in terms of theta. Now it's a little bit easier to look at. Now I can replace the second row of m and k. Now I'll have here 9mr times x1 double dot. I have here, I'll copy this in, that for my theta and replace this with mp, and that looks okay. And there's no x3 still. Looking at the k matrix here, I will have here a -2kr x1, and now actually the theta is next, a 2kr squared, and then the x3 term is going to be 2kr, and I don't need the k's because that's already taken care of. So -2r times the k, 2 times r times the k for the x3, and a 2r squared for the theta. And then the third row, looking at the m, that is going to still be 0, 0, and just little m. x3 double dot's the only double dot term. And then for the k matrix, I'll have to replace this. I will have here -2 times the k. I will have here 2r times the theta, and I'll have here, this will stay 5. Okay, so I get a different m matrix, a different k matrix, which should be expected as the equation of motion is different. And I can rerun all of this. And I have to put in my value of r now because that did not drop out. R is the 0.05. So I'll put my r value in, and I will need the r value down here as well. Right, so I have now the m and the k matrices, and we see we have them all as numbers. So let me just suppress that and run that. Okay, so the expectation is, even though the equations of motion were different, we are going to have the same natural frequencies and mode shapes because those quantities are coordinate invariant. It doesn't matter what set of 3 degrees of freedom we use, we're going to get the same values. So if we run this, I redefine my m sub k, And now let's find the natural frequencies and the mode shapes. Natural frequencies exactly the same as the first time. We're just using a different set of those 3 degrees of freedom to define our system. However, the natural frequencies are unaffected by this change. We're still getting here in descending order the 10.4 radians per second, 3.78, and the 0.514. So going back to the premise of the problem, we were given this system that turned out to have 3 independent degrees of freedom. We were originally tasked to find the equations of motion in terms of x1, 2, and 3. So we had to substitute out that theta using the coordinate mapping. And we saw that was related directly to x2 and x1. If we knew any 2 of those, we know the third one automatically. So we derived the kinetic energy and the potential energy in the system. In terms of first all 4 convenient degrees of freedom, did that substitution. We did that all in Mathematica here. We did our Lagrange's equations also in Mathematica. Let it do the differentiation step to get our 3 equations of motion in terms of the x's. Taking those scalar equations, we then transcribe them into our matrix form equation of motion, or equations of motion, filling in the stiffness matrix K and the mass matrix M. Ensured that they were symmetric, which indeed they were, which gives us some confidence that we did it correctly. We identified the system here, unforced, undamped, and 3 degrees of freedom, which is a multi-degree of freedom type of problem. And then just like we did for 2 degrees and multi-degree of freedom systems, we can find the natural frequencies, we can find the mode shapes by taking the eigensystem of m inverse times k. So we got in ascending order both in Mathematica and MATLAB. We had agreement of what those 3 natural frequencies were and what the 3 associated mode shapes were.